Scattered throughout the cosmos were celestial clouds of dust and gas known as nebulae, the grand cosmic nurseries where stars were born, and the cosmic graveyards where stars left their matter behind when they died. The word nebula came from the Latin word for cloud or mist, and the earliest astronomers used it to describe anything in the sky that appeared fuzzy rather than point-like. A category that once included galaxies, star clusters, and the actual nebulae before telescopes were powerful enough to resolve the difference. Today the term was more rigorously defined, referring specifically to clouds of dust and jets in the interstellar medium, the space between stars inside a galaxy, whose specific physical properties, energy sources, and relationships to nearby stars determined which category they belonged to. The four primary types were emission nebulae, reflection nebulae, dark nebulae, and planetary nebulae. But within and alongside those primary categories existed additional types: supernova remnants, protoplanetary nebulae, HII regions, and molecular clouds, whose individual properties told different and equally specific stories about the physical process that had created them. Here is every type of nebula, explained in full. Let's break this down. Emission nebula. Emission nebulae were the most visually spectacular of all nebula types, and the ones whose glowing colors had made them the most recognizable and most reproduced astronomical objects in the history of astrophotography. Clouds of ionized gas that generated their own light through the specific physical process of photoionization, the stripping of electrons from atoms by high-energy ultraviolet radiation from nearby hot young stars, and the subsequent release of energy as photons when those electrons recombined with the ions they had left behind. The most famous example of an emission nebula was the Orion Nebula, designated M42 in Charles Messier's catalog and located approximately 1,344 light-years from Earth in the constellation Orion, visible to the naked eye as the fuzzy middle star in Orion's sword, the only nebula visible without optical aid from a typical dark sky location. The Orion Nebula spanned approximately 24 light-years in diameter and contained a mass of gas and dust equivalent to approximately 2,000 solar masses, with the young star cluster known as the trapezium at its core providing the ultraviolet radiation that ionized the surrounding gas and caused it to glow in the specific wavelengths that gave the nebula its characteristic colors: the red of hydrogen alpha emission at 656 nanometers, dominating in long exposure photographs, the green of doubly ionized oxygen at 501 nanometers, creating the teal tones visible in composite multi-wavelength images. The specific mechanism of emission nebula light production was the mechanism of fluorescence at astronomical scale. The ultraviolet photons from the hot central stars carried enough energy to eject electrons from hydrogen, oxygen, nitrogen, and sulfur atoms in the surrounding gas, and those free electrons eventually recombined with ions at lower energy states, releasing the energy difference as visible light whose specific wavelengths corresponded to the specific atomic transitions involved. The Carina Nebula, NGC 3372, located approximately 7,500 light-years away and spanning approximately 300 light-years across, was one of the largest and brightest emission nebulae in the Milky Way, hosting the extraordinarily massive and luminous star Eta Carinae, a star with an estimated mass of between 100 and 150 solar masses that was one of the most luminous and most unstable stars in the galaxy, and whose eventual supernova explosion would produce one of the most dramatic astronomical events visible from Earth. The Bubble Nebula, NGC 7635, was an emission nebula whose specific visual appearance communicated the physical process producing it with unusual clarity. The spherical bubble of ionized gas surrounding the central massive star being the result of the stellar wind from that star pushing the surrounding interstellar medium outward in a spherical shell, the leading edge of the shell being bright in emission because it was where the shock between the stellar wind and the ambient gas was most intense. The James Webb Space Telescope's images of emission nebulae released beginning in 2022 revealed structures within these clouds at resolutions and sensitivities that no prior observatory had achieved. The Carina Nebula's edge in Webb's first released images showing individual protostellar jets, pillar structures whose tips were being eroded by radiation from the nearby massive stars, and young stellar objects embedded within the nebula's densest regions that were invisible in optical images, but luminous in the infrared wavelengths that Webb's instruments were optimized to observe. Hit the like and subscribe button to see more videos like this. Leave a comment on your favorite type of nebula. Let's get back into the video. Reflection nebula. Reflection nebulae were the physically simplest and the most directly analogous to everyday human experience of any nebula type. Clouds of dust and gas that did not generate their own light but were illuminated by the reflected and scattered light of nearby stars in exactly the same way that dust particles in a sunbeam or fog in a searchlight became visible by scattering the light source rather than generating light themselves. Reflection nebulae do not emit their own light but instead shine by reflecting the light of nearby stars. The physical mechanism being Mie scattering and Rayleigh scattering of starlight off the dust grains within the nebula, the same scattering processes that made Earth's sky blue. These nebulae tend to appear blue because blue light was scattered more efficiently than red light by the submicrometer dust grains within them, the same physics that gave Earth its blue sky being the physics that gave reflection nebulae their characteristic blue tones in astronomical photographs. The Pleiades star cluster, M45, the Seven Sisters, provided the most famous and most easily observed example of a reflection nebula in the entire sky, the cloud of interstellar dust through which the cluster was currently passing, reflecting the light of the cluster's hot blue stars in a way that was visible in long exposure photographs as a wispy blue glow surrounding the brightest cluster members. The Pleiades reflection in nebula was not physically associated with the cluster itself. The cluster was moving through a region of the galaxy that happened to contain pre-existing interstellar dust, and the coincidental alignment of the bright hot stars and the dust cloud was producing the scattering effect rather than any causal connection between the stars and the nebula. The Witch Head Nebula, IC 2118, located approximately 900 light-years from Earth in the constellation Eridanus, was a reflection nebula illuminated by the nearby supergiant star Rigel in Orion, the blue color of the nebula reflecting both the blue scattering preference of its dust and the blue color of Rigel itself, one of the hottest and most luminous stars visible in the night sky. Reflection nebulae were often found in close physical proximity to emission nebulae, the same regions of star formation that produce the hot young stars capable of ionizing surrounding gas to create emission nebulae also tended to have dense clouds of dust in which those same stars could create reflection nebulae by illuminating dust that was too dense or too distant from the ionizing star to become fully ionized. The Trifid Nebula, M20, located approximately 5,200 light-years away in Sagittarius, was a striking example of both emission and reflection components within the same overall nebula complex, the southern portion glowing red in hydrogen alpha emission, while the northern portion shone blue in reflected starlight, the physical boundary between the two regions being sharp enough to be visible in amateur telescope images. Dark Nebula. Dark nebulae were the counterintuitive members of the nebula family, clouds of dust and gas so dense that they did not emit or reflect any significant amount of light, but instead became visible by blocking the light of stars, emission nebulae, and other luminous objects behind them, appearing as dark patches or intrusions against brighter backgrounds in the way that a storm cloud was visible against a bright sky. Dark nebulae, also known as absorption nebulae, were clouds of dust and gas dense enough to obscure the visible wavelengths of light from objects behind them, the dust grains within them absorbing and scattering starlight so completely that the interior of a dark nebula was among the most optically opaque environments in the galaxy, a region where the visible light intensity dropped by factors of thousands to millions compared to the surrounding interstellar medium. The Horsehead Nebula in Orion was the most visually iconic dark nebula in the sky. Designated Barnard 33, it was a protrusion of dense molecular gas and dust extending southward from a larger molecular cloud into the bright emission nebula IC 434, its horsehead silhouette being one of the most immediately recognizable shapes in astrophotography. The horsehead's apparent shape was a coincidence of the perspective from Earth. The nebula's actual three-dimensional structure was simply an irregular, dense region of molecular cloud. The horsehead profile being what that structure looked like from the specific vantage point of the solar system's position in the Milky Way. Dark nebulae were classified using the Barnard catalog, compiled by astronomer Edward Emerson Barnard in the early 20th century, who photographed dark regions of the Milky Way systematically and cataloged them as absorbing clouds rather than empty regions of space, His recognition that dark patches in the Milky Way were something rather than nothing being one of the foundational insights of interstellar medium astronomy. Bok globules, named after astronomer Bart Bok, who drew attention to them in the 1940s, were small, nearly spherical dark nebulae, typically 1 to 50 light-years in diameter and containing between 1 and 1,000 solar masses of gas and dust, representing the densest and most compact dark nebulae and the objects most likely to be in the immediate pre-collapse stage before star formation began. Many different types of molecules have been detected on the tiny dust grains in dark nebulae, complex organic molecules including amino acid precursors, simple sugars, and the building blocks of RNA had been identified in molecular clouds, communicating that the chemistry of life's ingredients was not confined to planetary surfaces, but was distributed throughout the interstellar medium in the dense clouds where stars and planetary systems formed. Planetary nebula. Planetary nebulae were the cosmic inheritance that medium-mass stars left behind when they died. The shells of gas and ionized material ejected by stars in the later stages of their evolution as they transitioned from red giants to white dwarfs, expanding outward from the central stellar remnant in glowing clouds whose specific shapes, colors, and structures encoded information about the dying star's mass, rotation, magnetic field, and whether it had been accompanied by a binary companion during the final ejection. Despite their name, they had nothing to do with planets. The name arose because of their round appearance through early telescopes, which caused astronomers like William Herschel to compare them to the disc-like appearances of the giant planets Uranus and Neptune before those planets were well understood. The Ring Nebula in the constellation Lyra, M57, located approximately 2,300 light-years from Earth, was the most observed and most studied planetary nebula in the northern hemisphere sky. Its ring-like appearance in small telescopes representing the edge-brightened shell of ionized gas that surrounded the central white dwarf whose ultraviolet radiation drove the nebula's luminosity. James Webb Space Telescope images of the Ring Nebula released in 2023 revealed an extraordinarily complex internal structure, concentric rings of material suggesting multiple ejection events, a central cavity filled with hot gas, and a detailed mapping of the temperature and density structure across the nebula that confirmed theoretical models of the ejection process with unprecedented precision. Our sun would probably produce a planetary nebula in approximately 5 billion years. The specific statement connecting the astronomical phenomenon being described to a process that would eventually affect the solar system itself, the sun's eventual red giant phase expected to expand the star to approximately the current orbit of Earth before the outer layers were shed as a planetary nebula and the core contracted to a white dwarf roughly the size of Earth. Planetary nebulae had a short astronomical lifespan of approximately 10,000 years, the expanding shell eventually becoming too diffuse and too cold to maintain its ionization and luminosity, dispersing into the surrounding interstellar medium and returning the material to the galaxy's gas reservoir for incorporation into future stars and planetary systems, the approximately 3,000 known planetary nebula representing only the current snapshot of a population that was continuously forming and dispersing on timescales short compared to the age of the galaxy. Supernova remnant nebula. Supernova remnant nebulae were the most energetically extreme nebulae in the universe. The clouds of material produced when a massive star ended its life in a supernova explosion, the ejected stellar material expanding outward at velocities of thousands of kilometers per second and sweeping up surrounding interstellar medium in a shock wave, whose energy maintained the nebula's luminosity for thousands to tens of thousands of years after the original explosion. A supernova remnant was a type of emission nebula, the ionization of the shocked material by the energetic shock wave, producing the emission line spectra that classified the nebula as an emission type. The specific mechanism of ionization being the conversion of kinetic energy to thermal energy at the shock front rather than the photoionization by a central star that drove ordinary emission nebulae. The Crab Nebula M1, located approximately 6,500 light-years away in the constellation Taurus, was the most studied supernova remnant in the sky and the object whose historical record was unusually complete. The supernova that produced it having been observed and recorded by Chinese and Islamic astronomers in July 1054 CE as a new star visible in daylight for 23 days and in the night sky for approximately 2 years. At the center of the Crab Nebula was a pulsar, a rapidly rotating neutron star that was the collapsed core remaining after the supernova, spinning at approximately 30 times per second and radiating energy across the electromagnetic spectrum from radio waves to gamma rays. The pulsar's wind of relativistic electrons and positrons, inflating the nebula's interior and producing the blue synchrotron radiation visible in the nebula's core. The Veil Nebula in the constellation Cygnus was the remnant of a star that had exploded approximately 8,000 years ago, the shockwave having expanded to a diameter of approximately 110 light-years, large enough that different sections of the shock were catalogued as separate objects before their common origin was recognized. The filamentary structures visible in the veil, representing the complex turbulent interface between the supernova ejecta and the surrounding interstellar medium. For a few days, a supernova emitted as much energy as an entire galaxy, and when it was all over, a large fraction of the star was blown into space as a supernova remnant, whose expanding shockwave was a critical mechanism for enriching the interstellar medium with the heavy elements synthesized in the supernova, distributing iron, nickel, silicon, and all elements heavier than iron produced in the explosion into the gas from which the next generation of stars and planetary systems would form. Protoplanetary nebula. Protoplanetary nebulae were the transitional objects that occupied the brief and spectacular evolutionary phase between a star's red giant stage and the formation of the planetary nebula that marked the completion of the ejection process, a phase lasting only a few thousand years in astronomical terms, but whose specific physical and chemical properties during that transition encoded information about the processes connecting two of stellar evolution's most dramatic stages. A protoplanetary nebula was a type of reflection nebula that consisted of gas ejected from red giant stars late in their life. This gas reflected the light of the red giant rather than being ionized by it, the central star during the protoplanetary nebula phase not yet being hot enough to ionize the surrounding gas and produce the emission spectrum of a true planetary nebula. The Egg Nebula, CRL 2688, located approximately 3,000 light-years from Earth, was one of the most studied protoplanetary nebulae in the sky. Its concentric shells of dust and gas surrounding the central star being illuminated in reflected starlight and showing the layered ejection history of the mass loss process that had been steadily stripping the star's outer layers for thousands of years before the ejection accelerated to produce the protoplanetary nebula stage. The Rotten Egg Nebula, also known as the Calabash Nebula, designated OH 231.84.2, was a protoplanetary nebula in an unusually early stage of the transition, still retaining the elongated bipolar morphology of gas being ejected at high velocity before the central star had heated sufficiently to ionize the material into a full planetary nebula. The extremely high outflow velocities measured in this object, approximately 180 kilometers per second, representing some of the fastest gas flows observed in any protoplanetary nebula and providing direct evidence of the violent acceleration process that accompanied the transition. The protoplanetary nebula phase was significant because it was during this brief window that much of the chemical complexity of the gas was established. The dust grains forming in the cooling outflow from the red giant surface developed the complex molecular chemistry that would eventually be distributed into the interstellar medium when the planetary nebula dispersed, contributing the carbon-rich and oxygen-rich dust grains that were the building blocks of the next generation of planetary systems. HII region and molecular cloud nebula. HII regions were the most massive and most physically significant of all nebula types in terms of their role in shaping the large-scale structure of galaxies, enormous clouds of ionized hydrogen gas whose luminosity was powered by clusters of hot, young, massive stars embedded within them, the ultraviolet radiation from those stars ionizing the surrounding gas across regions spanning hundreds of light-years and creating the brightest individual objects visible in external galaxies at optical and radio wavelengths. An HII region was a type of emission nebula consisting of an area within a giant hydrogen gas cloud that had collapsed under gravity to create a star-forming region. These newborn stars then ionized and illuminated the gas and dust around them, the combined ionizing output of dozens to hundreds of massive young stars, producing a region of ionized gas whose luminosity far exceeded that of any individual star. The name HII referred to the ionized state of hydrogen, HI being neutral hydrogen, HII being singly ionized hydrogen, in which the single electron had been stripped away by the ultraviolet radiation from the central hot stars. The Lagoon Nebula, M8, located approximately 4,100 light-years away in Sagittarius, was one of the largest and brightest HII regions visible in the night sky, spanning approximately 110 by 50 light-years, and being the site of active star formation with young stellar objects embedded within its densest clouds. The Tarantula Nebula, 30 Doradus, located in the Large Magellanic Cloud approximately 160,000 light-years from Earth, was the largest and most luminous HII region in the local group of galaxies, spanning approximately 1,000 light-years in diameter and containing the most massive stars known to astronomy, including the star R13XA1 with an estimated mass of approximately 150 solar masses that was among the most luminous individual stars in the observable universe. Molecular clouds were the cold, dense giant structures within the interstellar medium from which HII regions and all star formation ultimately originated, clouds of molecular hydrogen, carbon monoxide, and complex organic molecules, whose temperatures of 10 to 30 Kelvin and densities millions of times higher than the surrounding interstellar medium provided the physical conditions necessary for gravitational collapse into the protostars that became the hot young stars that then ionized the surrounding gas to create the HII region. Diffuse nebulae, the broadest category of nebulae, were the largest of all nebulae and made up of primordial hydrogen, helium, and traces of other elements. These were the raw material of the universe's stellar population, the reservoirs from which stars had been forming since the first galaxies coalesced from the primordial gas of the Big Bang, and whose continued existence and continued star formation activity was the mechanism by which the Milky Way and all other spiral galaxies maintained their populations of young hot stars and their spectacular spiral arm structures across billions of years of cosmic time.